Hi, everyone. Thanks for coming. So today we're going to discuss a new solution for accelerating shuffle, which is a huge pain for a lot of data scientists. And we're using a new technology, which is not so new anymore. It's becoming very popular, and it's slowly becoming a commodity these days. And I think this is a great time to adopt this kind of technology, and we'll see soon why. So just as a teaser before we move on and see how we do this kind of acceleration. So TeraSort is a very popular big data benchmark. And we get these awesome results with the RDMA acceleration for Spark. And we get this 1.45x speed up just by replacing the shuffle engine. So TeraSort is exactly the same as you used to see in other benchmarks. There's no tuning, nothing at all, just replacing the shuffle engine with this new RDMA accelerated engine. So a few words about Mellanox, and that's going to be, these 4 lines are the only kind of marketing stuff you're going to see in the slides. So Mellanox was founded in 1999. It's an end-to-end designer and supplier of interconnect solution that goes for network adapters, switches, system on a switch, devices, cables, silicon, and software. Networking products by Mellanox, they run on 10 to 400 gigabit per second. So it's all the way from mid-range to boutique high-end kind of devices. And that goes through all the network adapters in the compute system, cables, switches, gateways, and back to the storage again with network adapters and so on. And that goes for Ethernet and InfiniBand as well, depending on the kind of enterprise that and the interconnect that it chooses. So what's RDMA? RDMA stands for Remote Direct Memory Access. It basically lets you read and write from to remote memory locations. All you need is an address in order to fetch stuff from another machine's memory, instead of going through the whole TCP stack, creating packets, allocating buffers, doing flow control, and all those sort of things that you have to do in the kernel that takes precious CPU. So in this chart, we can see that we have this kind of buffer in this Java application, just random Java applications. And instead of going through the sockets, doing this kind of context switch where we call system calls to go to the kernel, go through sockets, TCP/IP, driver, and only then get to the hardware. And all these requires data copies, CPU-intensive manipulation of data, and so on. And instead of that, you get a user-level interface that you can just transmit and receive data without going through the kernel. You go directly to the hardware from user space. And this is something that is unique for RDMA. There are several different technologies that try to do something similar, but RDMA makes it as simple as it can possibly be. So you instantly get 0 copy. It's a direct hardware interface, so as we just said, it bypasses the kernel, no TCP/IP stack, nothing goes into the I/O path in terms of going through the software stack. Flow control and reliability is offloaded in hardware, whereas in TCP/IP, it's handled by software and takes precious CPU cycles. It has sub-microsecond latency, and this is something that is very unique to this kind of technology. And there are other interconnects that can do stuff like that, but TCP/IP, which is the traditional way to transfer data, doesn't have any of that. It's supported on almost all mid-range, high-end network adapters. It's not only Mellanox specific technology. It's available on other vendors of network adapters as well. And it has growing cloud support. It's already supported in Microsoft Azure and on A and H instances. So it's also gathering cloud support. So a few words about hardware acceleration in big data and machine learning platforms. So hardware acceleration adoption is growing very fast. GPU integration is almost anywhere now. In all frameworks, like every framework you can think about has support for GPU acceleration. ASIC is picking up speed very quickly as well. And RDMA, as part of this kind of hardware acceleration, is also picking up speed and is integrated already with the mainstream code of popular frameworks. For example, TensorFlow, Caffe2, CNTK, and there's a bunch more. And we think that this is Spark's turn to catch up with this and allow this kind of acceleration. So before we move on and discuss more about how the Spark Shuffle engine works and how we accelerated with RDMA, I want to give an intro of how Shuffle works under the hood in Spark. So we'll start with defining what are the properties which are different between MapReduce and Spark, and that gives Spark its uniqueness in the fact that Spark stores everything in memory. So Spark's in-memory model basically changes everything for Shuffle. So in both Spark and MapReduce, map output is saved on the local disk, which is usually in buffer cache, aka memory. Now in MapReduce, the map output is copied over the network to the destined reducer's local disk. In the Spark case, the map output is being fetched by the readers and then saved directly into memory. So that gives us, in the Spark case, a memory to network to memory transfers, and that's a perfect fit for RDMA. So a few words on how Shuffle works in Spark. And this is without RDMA, it's just a background. So Shuffle is broken down into two stages. We have the map and reduce phase. And in the map phase, we start by having some kind of input. So this input can be files, traditionally files coming in from HDFS. Now, when we perform a shuffle, we define a partitioner. This partitioner takes these chunks of data and colors them. In this case, I choose colors instead of numbers or anything to make it more clear. So this partitioner colors the chunks of data, which will then be fed into the reducers. And the reducers will have a specific color or a specific partition. So we have the input coming into the map tasks. And the map output will basically take the input for that specific map task and sort it so that all of the colors will have a continuous range. And we're basically going to have one range of colors where all chunks of the specific color will be continuously in the data output. So the next step will be to save those to a local file. As we said, this is buffer cache and usually memory. And the map statuses, which basically represents the chunks of data in terms of what partition is where and the size of each partition, are then being communicated into the driver, which aggregates all this information. Now, the driver will then feed this information into the reducers, which the reducers now represents the actual partitions that we did all the work for the mapping. So if we consider the blue partition, then this partition will now fetch all of the relevant blocks for the blue partition. So we have, basically after the fetching on the reading phase, we end up with a continuous chunk that holds all of the specified partition data in one big buffer of memory, or sometimes it's spread into smaller buffers. It really depends on how the data is being broken down. Now, the next step will be to follow up with the compute phase, since now we have all of the data being fed into the actual reduce function. So I'd like to dive in a little bit deeper into how the shuffle read protocol works. So we're in the reducer, and we're trying to fetch the blocks and retrieve them into the reader, which will then forward them to the compute side. So we start with a partition that we would like to retrieve. So the shuffle read starts with a partition number and requests the map statuses from the driver. So the driver that aggregates all this map status data now returns a list of blocks which represents each block location and its size and where it's located. So with this metadata that we got from the driver, the reader will then group the blocks by their writer. And when I say writer, I mean executor. So it really depends on the number of executors that you have. And this reader is also an executor by itself. Now, when it groups the block locations by the writer, it will then send a fetch request with these list of blocks to each writer. So this step actually happens for each and every writer that has the data that we're looking for. Now, the next step will be for the writer to locate the blocks and set up as a stream and send back the stream ID. Now, the reader has a stream ID for each executor that it sent the fetch block request, and it's now ready to fetch each specific block one by one. So this step 6 and 7, these happen for each and every block. And there's a lot of messaging going here over the RPC messaging platform. Now, each writer in return will locate the block that was requested by the reader and will send it back. And once it gets back, this is where the data is now ready, and we can move forward to the reducer function. So a little bit about the cost of shuffling. So shuffling is very expensive in terms of CPU, RAM, disk, and network IOs. People try to avoid it as much as they can, and sometimes very complex applications that can be written in a very simplified way become very complex because you try to avoid shuffles as much as possible. So with these speedy shuffles, accelerated and so on, we can relieve developers of this requirement and try to avoid these kind of concerns by just making shuffle faster. And this way we can simplify applications. So with all this in mind, now I'll show you how we accelerate shuffle with RDMA. So our solution is what we call the SparkRDMA shuffle plugin. And we started with defining a very specific design goals, which are very important to bind to. Otherwise, it will be very difficult for user to adopt. So clearly, the first goal will be to demonstrate significant improvements over standard Spark. We would like to have seamless acceleration for shuffles with RDMA without any kind of functional limitations. It has to be easy to use and to deploy and minimize the code impact. So we want to limit the code changes only for the part where you actually do the transfers. And the design approach that we came up with is we've decided to switch the entire shuffle-related communications and do it with RDMA. So the RPC messaging for metadata transfers, which are the map statuses and so on, everything is on RDMA. And of course, the block data itself is with RDMA. So SparkRDMA is an independent plugin. It implements the Shuffle Manager interface. It has no changes to the Spark code. You can use it with any kind of existing Spark installation, either Cloudera, HDP, or standard Spark. It reuses Spark facilities as much as possible. So we, again, want to minimize the impact on the code and maximize the reliability and testing that Spark already went through. So RDMA functionality is provided by Disney. Disney is an open source Java interface to RDMA user libraries. It was first introduced by IBM, and today it's maintained in the open source community. You can check it out in this link. And most importantly, no functionality loss of any kind. So SparkRDMA supports everything that you can do with standard shuffle. That's compression, spilling to disk, and recovery from failed map and reduce tasks. So let's dive in a little bit deeper to how we plug it into existing Spark installations. So Sparks today allows for external implementations of the shuffle managers to be configured using a very simple handle that you put in your Spark configuration file or code or whatever how you pass this kind of configurations. So this interface allows proprietary implementations of shuffle writers and readers, and basically allows to offload all of the shuffle transfers into a separate component. And this is what we use in SparkRDMA to seamlessly accelerate the shuffle transfers. So if we examine the SparkRDMA components compared to how Spark is built today, so the default shuffle manager is the sort shuffle manager, which wraps up writers, the bypass, unsafe, and sort shuffle writers. Now, what we did in SparkRDMA is we reused the unsafe and sort, and we didn't reuse the bypass since we found that it doesn't perform that well, and we already see a lot of discussions going on that it's going to be deprecated anyway. So what we did is we created a very slim writer that basically wraps the existing writer in Spark. And the reason that we did that is we wanted to write and store the shuffle data exactly as standard Spark does today. We didn't want to actually change data. So other than that, we implemented a new shuffle reader and shuffle block resolver that basically do the transfers over the RDMA transfer that we're trying to fit in here. So let's go back a little bit and show how the protocol now changes when we introduce RDMA. So this is the standard protocol again. And we can see that there are a lot of steps here, lots of messaging going on. And what we did in the RDMA implementation for the read protocol, we tried to make it as slimmer as possible and reduce the amount of messaging and improve CPU utilization and so on. So in the RDMA implementation, everything stays exactly the same until this part where we have the block locations coming in from the driver. Now, the next step is we have a list of block locations where we piggyback the map statuses with the addresses for the block locations. So basically, we have remote addresses for memory with the block locations we're trying to fetch. So we can just RDMA read them without going through all this messaging that we saw in the standard implementation. So the next step will be to just read these pieces of memory. And since we don't have any kind of software involved here, then the writer doesn't have any kind of operations in Java or in software in general. So everything is offloaded by hardware, and that reduces a lot of the load on the writers. And again, readers and writers are basically executors. So this reader is also a writer, and this writer is also a reader. So that lets that writer to do its read tasks much faster. And the next step, we just have the data ready now, and we can forward it to the reducer. So let's compare those side by side. So we can see here that everything stays exactly the same until the part where we have the shuffle block locations. From this part on, it changes. So let's do a zoom in to the parts that are different between TCP and RDMA. Now we can see here that in the standard case, we have one message going to each writer, and writer returns a message after it does its own kind of bookkeeping and stuff. And then the blocks are being requested one by one. The writer needs to process these requests and return them. So there are huge amount of messages going on here. If you increase the number of partitions, then there will be more messages. So it becomes very heavy on CPU and so on to do only this kind of shuffle transfers. So in the RDMA case, we just read directly from the writers without any kind of intervention from the writers themselves, and the block data is just ready right away. Now, we can see that on the server side, there's no action whatsoever. So there's zero CPU. And that gives us also another thing that is very important in Spark and in Java in general. So Java is very tough with its users because of garbage collection. Now, since we don't have any kind of CPU going on here, then even if the writer is blocked by GC pause, then it doesn't affect the reader, which can still fetch its blocks without any trouble. So that's a huge improvement, that the fact that the reader is being unblocked. There's no buffering on the writer because there's no action. It's just being read directly from memory and offloaded by hardware. And on the client side, we have instant transfers and, of course, reduced messaging and direct unblocked access to the remote blocks. So with all of these in mind, we get a lot of benefits from using SparkRDMA. So we have substantial improvements in block transfer times. Latency and total transfer time is improved significantly, and that reflects on the runtime of jobs. Memory consumption and management is reduced, so memory pressure is much less noticeable when you compare it to shuffle on TCP. CPU utilization is reduced, so you get extra cycles that can now be used for the actual reduced task in mind. It's very easy to deploy and to configure it. Just everything is packed into a single jar file. You can just configure it, and that's it. Put it on your class path, and you're done. The plugin is enabled through a simple configuration handle, as we showed. And for those who would like to do some kind of advanced tuning, then it also provides some finer tuning through a set of configuration handles. And the most important thing is when you introduce new kind of technologies and accelerations, it's very important to do it slowly and in a safer manner. Now, the fact that it's configured per job, you can just test it with some jobs that you think are shuffle intensive and see how it goes. You don't have to deploy it on all of the cluster on all kind of jobs. You can just deploy it on some jobs and see how it goes and go from there and proceed to more and more jobs. So let's continue to the interesting part. So we see that in High-Bench TeraSort, which is the plain version that you get from GitHub, there's no changes to the actual code whatsoever. There's no special tuning here. Just plain Spark with plain SparkRDMA with this single configuration handle. We see this 1.45x speed up, which is very easy to get. All you have to do is just use this kind of plugin. You don't have to change your application. You don't have to tune anything. In most cases, you already have hardware that supports it. So it's very easy to deploy and to test and see, if you get this kind of improvement and earn this kind of speed up without a lot of effort. So the workload that we used is a 175 gig High-Bench TeraSort on HDFS 2.6.0 without any kind of replication. This is Spark 2.0 with one master, 15 workers. This is standalone mode. It also works with Yarn, obviously. So we have 28 active Spark cores on each node, and that's 420 total. These machines are kind of old, and still we see this huge improvement in runtime. And this is the total runtime of the job. This isn't just the shuffle part of the job. So we also ran a few tests on GroupBy. So GroupBy, in this case, gains a 1.39x improvement. And that's very interesting because GroupBy doesn't have any kind of storage. There's no HDFS at all here. This is all Spark. And still, when you rule out the storage, you still get this kind of speed up. And that makes it more appealing for applications that for example, streaming application and so on that doesn't rely on storage access. We ran it with 48 million keys, each of 4K bytes. And the workload is 183 gigs. Other than that, all of the machine configuration is exactly the same. So what's next for SparkRDMA? SparkRDMA was officially released less than a month ago. It's publicly available on GitHub, open source. You can just grab it and use it. You don't even have to compile it. All of the pre-compiled binaries are already there. If you want to compile and contribute, we welcome any kind of PRs or anything. We are working on integrating SparkRDMA into upstream Apache Spark. There's an open discussion in the community for that. And going further, we're looking into extending the RDMA capabilities in Spark to more components, for example, RDD access over the network and broadcasts. And also, we're working on another project for RDMA acceleration for HDFS. So open source, SparkRDMA is available on GitHub. You'll find there a quick installation guide and wiki pages for advanced settings for those who are interested, and more information about the actual code and components and so on. We ask that you support us in integrating SparkRDMA into mainstream Spark. And we have this Jira open here, and we'll appreciate any support from anyone that would like to vote for us or present any questions or anything else. Feel free to reach out in my email, whatever you need, suggestions, questions, everything is welcome. Thank you.
OK. Thank you so much for that nice presentation. I think we still have a few minutes for questions. Does anybody have a question? You can walk up to the microphone in the aisle.
Very interesting talk. So one of the obvious questions, which is clearly there were two kind of optimizations that happened. One was using RDMA, and the second was batching up of a lot of block and their stream ID operations, right? Mm-hmm. Would you have a split of how much each of the optimization contributed?
So our original, well, actually the iterator that we're using is heavily based on the standard iterator that Spark has. Okay. So the actual way we fetch the data, besides that it goes over RDMA, there's not much difference comparing the two. So the chunks are the same size. There's no difference. Only the actual transfers are different.
OK. The number of calls that happen for the actual transfers.
Exactly. Yeah.
OK. Got it. Another small question I had was, is there any special cluster configuration we need to do to enable RDMA? You said there were some Disney APIs that need to be used. Are they packaged along with the RDMA shuffle as a plugin, or do we need to do something else?
So Disney is packed within SparkRDMA dependencies. It does have a JNI library that you have to deploy, and we are working on putting it into the Spark dependency as well. So by the end of the year, we're going to have a package that you can just deploy, and that's it. Cool. For now, you have to deploy the jar file and the .so file, which is it's a
JNI part of it.
Yeah,
the
exactly.
Part. Thanks. Yep.
Sure.
Hi. So I had a question about the results you showed for GroupBy. You said there was no disk access. Can you explain why then for the speed up?
So it's not so there's no remote storage access. So in GroupBy, it's not like you read something from HDFS and write back. So the data is being generated on the nodes themselves, and then it's being shuffled and sent back to the nodes for reducing.
OK, so there's still a shuffle operation.
Yeah, there's still shuffle, but no storage access on the remote storage.
Thanks.
Sure.
I apologize if you covered this in the first part of the talk. I missed it. But the point, of course, of a shuffle manager, if you're in dynamic allocation mode, is the shuffle service can kind of like store results in the case you actually lose an executor. Have you tested like impacts in that kind of scenario where executors are dropping out and being replaced or scaled up and down?
So in the dynamic allocation situation, this is not supported because you have to use the external shuffle service. Now, it is supported if you don't have dynamic allocation, and in that case, if executors crash, then Spark will automatically start them and reproduce the map data. We're also working on researching a way to implement our own external shuffle service so we can support users who use dynamic allocation. And this is something we're looking into doing through the first quarter of 2018.
Thank you.
Sure.
Okay, that's all the time we have. I want to thank our speaker and give him a hand.